Hi, I'm Ben, and welcome to Rust Curious, where I explain Rust carefully. At rustcurious.com you'll find this map of the type system called the elements of Rust. We've been working our way through the compound types. In video number 4 we covered tuples and structs, video number 6 was all about enums and unions, and now it's time to do arrays. This is the fixed length array type. It's a bit like a tuple, but all the elements must have the same type. So you can index into it, you can iterate over it, you can do all the things you'd expect to do with an array. It's pretty straightforward. The T is the element type, and the N after the semicolon is the number of elements. The length is part of the type, so the number of elements is fixed at compile time. If you have an instance of a fixed length array, then you definitely have that many elements, and the representation is just those elements next to each other in memory. We're also going to look at a type from the standard library called vec. Vec is short for vector. It's a dynamic array, meaning it holds a variable number of elements. Vec is a struct, and the struct itself has a fixed size in memory. However, it can handle any number of elements because it owns a block of memory that is dynamically allocated on the heap, and that allocation can grow as needed at runtime. So, for example, you can call a push method that appends an element, and it grows the allocation if it needs to. So we have distinct types for fixed length arrays versus dynamic arrays, and it would be cool if we could write functions that work with data in any array type. Rust has the perfect solution for that, and it's called an array slice. If we follow this line to the right of the fixed length array, we pass through something called the unsized array slice, and then where it intersects with the borrowed reference types, we find the shared array slice and the mutable array slice. These types are borrowed references that point to some number of elements, and they give us a lot of flexibility when dealing with arrays. Curious? Okay, so first I'll show you how to use fixed length arrays, and we'll see some differences depending on whether the element type in the array can be copied or not. Then we'll write some functions that take array slices, meaning the function gets a borrowed reference that can point to any number of elements. Then we'll introduce vec, which is the dynamic array type from the standard library. Vec can own any number of elements allocated on the heap, and you can access those elements as a slice. And finally, I'll leave you with a little practice exercise to get those fingers moving. Alright, let's get into it. Let's make an array. Inside some square brackets, I write a list of values separated by commas, and I've got myself an array. This expression produces a fixed length array, so if I wanted to make the type explicit, it would look like this. The element type is i32 and the length is 4. And yes, it looks a little bit strange at first to have that semicolon inside the square brackets, but you get used to it. And there's a good reason they didn't use a comma there, because as you'll see in a minute, that would have been ambiguous. To make an array, you have to provide a value for every element. You can't have uninitialized memory, at least not in safe Rust. So let's say I want a big array like a buffer of 1000 bytes. I've chosen U8 as the element type and 1000 as the length. But to create an instance of this array, do I have to write out 1000 zeros separated by commas? No, I can instead provide a single value, 0, that gets copied into every element of the array. And now you can see how the semicolon makes this unambiguous. The number after the semicolon is the length. Now, we don't have to make these array types explicit, so let's leave them out for now. Alright, let's access some array elements. As you'd expect, we can index into the array using square brackets, and of course the array index is 0 based, so in a 4-element array, index 3 will access the last element, so x gets the value 8128. If we want to assign to an array element, then the whole array needs to be mutable. So now buff is a mutable variable, and we can assign to elements in the array. When you index into an array, the index must be a usize. This function takes a parameter I and uses it to index into the array. I is a usize, and a usize is an unsigned integer with the same number of bits as a pointer on that platform. On a 32-bit system, it's 32 bits. On a 64-bit system, it's 64 bits. So even if you have a huge array that takes up most of your address space, a usize is always big enough to reach any element. Anytime we index into an array, the compiler inserts a bounds check on the index, which will panic if it's out of bounds. Rust is not going to let you access out-of-bounds memory. So if you call this function with index 4, that's past the end of the array, so it'll panic. Video number 3 is all about panics if you'd like to know more. To iterate over all the elements in an array, we can use a for loop. When I say for x in array, on each iteration, x is assigned the next element, and I can print it out. Right now, we're passing the array by value into the for loop, so x is assigned the value of an element from the array. And of course, integers are copyable, so this array type is also copyable, and we can continue to use the array afterwards. What if we have an array of strings? This is the dynamic string type, and it can't be copied because it owns a heap allocation. That means this array is also a non-copyable type. So when I pass the array into the for loop by value, it's a move. The loop consumes the array. If I try to use the array again after the loop, that's an error. Use of moved value. The array was moved into the for loop and we no longer have it. What we really want here is to iterate over the array by reference instead of by value. I'll show you that in a few minutes when we talk about array slices. Earlier, I showed you how to construct a large array by copying a single value into all the elements. This expression produces an array of 1,000 zeros. What if you need a large array with an element type that can't be copied? Here I'm trying to construct an array of 100 strings. Will this compile? No. We get an error that says the trait copy is not implemented for string. String can't be copied, but it can be cloned. The standard library provides this function, arrayRepeat, which takes a value and clones it as many times as is needed to make the array. So that's one option. It works with any type that has the clone trait. Another option is to use arrayFromFunction. This function takes a closure, which it calls repeatedly to make all the elements. There'll be a whole video on closures, but briefly, this closure expression is like a nested function. It takes a single parameter, I, which is the index we're up to, so it's a usize, and the body of the closure has to return a string for the element. This closure gets called 100 times, once for each element. The cool thing about this is the closure can return a different value for each element. So instead of filling the array with hello, we could use that parameter I to construct a string that contains the index. The format macro is just like println, but instead of writing to standard output, it returns a string. So this array now contains strings that say element 0, element 1, element 2, etc. And there's no clone happening here, so this can be used with any element type. Okay, let's access an element of this array of strings. If I index into the array and try to read that element into a new variable, I get an error. Cannot move out of type, string 100, a non-copy array. Cannot move out of here. Move occurs because array element has type string, which does not implement the copy trait. And that makes sense, right? We can't copy the string out of the array because it's not copyable. We can't move the string out of the array because then that part of the array would be invalid. We need some other way to access the element, and the error message goes on to make some suggestions. Consider borrowing here with an ampersand to take a shared reference to the element. Or consider cloning the value if the performance cost is acceptable. Well, I think I like the first suggestion better. So now x is a shared reference to a string. It points to the string in place in the array. I can read from it, I can print it out, I can pass that reference to a function, whatever. By the way, if all I want to do is pass it to println, I don't actually need the ampersand to take a reference. I can just pass it directly to println. Why does this work? Why isn't this a move? Well, because the println macro takes a shared reference to each of its arguments. Similarly, if I want to call a method on an array element in place, I can do that without explicitly taking a reference. The len method takes self as a shared reference, so when I call len, I'm implicitly using a shared reference to the string in the array. Cool, how about mutating array elements? If I make the whole array mutable with letMut, then I can take a mutable reference to an element. I have exclusive access to the string, so I can mutate it in place in the array. If I call pushString, then this will append to the string, so now the string at index 0 says element 0 is first. And again, if I'm just calling a method, I can let the mutable reference happen implicitly with the method call. The pushString method on string takes a mutable reference to self, so this just works. Okay, we've seen how references to individual array elements can let us work with those elements in place in the array. What if we want to call a function and pass a reference to all the elements in the array? I could write a function that takes a reference to a fixed length array. This works, but it only works for arrays of that specific length. I want a function that can work with arrays of any length. In C, it's very common for a function to take a pointer to the start of an array along with a separate parameter for the length of the array. For example, this is the write function for writing bytes to a file descriptor. Buff is the pointer to the start of the buffer, and nBytes is the number of bytes. Of course, with these as two separate parameters, it's up to the programmer to make sure that the pointer and the length correspond. Otherwise, you can easily cause an out-of-bounds access that can turn into a crash or a security vulnerability. In Rust, we have a single type that wraps the pointer and the length into one thing, and it's called an array slice. So here's the write method for files in Rust. It has a single parameter called buff, and it's a shared array slice, ampersand square brackets U8. Under the hood, this type contains a pointer and a length. It points to the start of the slice, and it knows how many elements there are. So let's say I have a fixed length array with 12 integers, and I want to pass it to a function that can take an array slice of any length. If I just take a reference to that array, then I have a pointer that points to the start of the array. The length is still fixed because the information about the length of the array is still in the type of this reference. But I can implicitly coerce that reference into an array slice. The array slice is like a little struct with two fields, one for the pointer and one for the length, in this case 12. The length field is represented as a usize, which is the same size as a pointer, so an array slice is twice the size of a regular pointer. Array slices are sometimes called wide pointers for that reason. Remember, an array slice is just a reference type. It doesn't actually own the data it points to. So now that we're carrying the length around in a field that could be anything at runtime, we can write a function that operates on an array of any length. This total function takes an array slice of integers and adds up the values. The parameter slice is a shared array slice of i32s. And when I say for x in slice, I get an iterator that produces a shared reference to each integer. So on each iteration, x is a shared reference to an i32. I dereference it with *x to get the value of the integer and add it to the total. To call this function, I can start with an array of any length. I just take a reference to the whole array and pass it to the function. And that reference is implicitly converted to an array slice because that's the parameter type of the function. We can also make a slice that covers part of an array instead of the whole thing by indexing into the array with a range. The range 2.8 covers the elements from index 2 up to but not including index 8. So now the picture looks like this. The pointer is pointing at index 2 in the array and the length is 6. This range expression 2.8 explicitly specifies the start index and the end index, but those are both optional. If I leave out the start index, then .8 means everything from the start up to but not including index 8. If I say .equals 8, that means everything up to and including index 8. If I say 2.equals 8, that means the range from index 2 up to and including index 8. If I specify the start but not the end, then 2. means everything from index 2 to the end. And if I leave out the start and the end, then the range ... just means everything. It's the same as just using the reference to the whole array and coercing that to a slice. So now you've seen that arrays can be indexed with different types. If you want a single element, then you index with a usize, but if you want a slice, then you index with a range. Each of the range expressions you just saw has a different type, and those types are on the Elements of Rust down in the bottom left corner. And you might notice these are generic types. They have a type parameter t in angle brackets. That's because different collection types use different index types. So you index into an array with a U size, but a B-tree map might be indexed with something else. We'll talk more about generic types in the next video. Okay, so we've seen shared array slices. What about mutable array slices? Well, they work in just the same way. This function, updateEach, takes a mutable array slice, ampersand mut, square brackets i32, and it adds the value k to each element in the array. So when I say for x in slice, on each iteration, x is assigned a mutable reference to an element, and we can increment each integer in turn by dereferencing x. Calling this function is just like before, but this time we're starting with a mutable reference to the array. I can pass a slice of the whole array by letting the mutable reference coerce to a mutable array slice, or I can pass just part of the array. So here I'm calling updateEach twice, with the first half of the array and then the second half of the array. I'm indexing into the array with a range expression to produce a mutable array slice that covers part of the whole array. Now, here's a question for you. Will this compile? This time I'm taking a slice of the first half and calling it A, and a slice of the second half and calling it B. And I'm holding both those slices before I call updateEach on each of them. Now, these ranges are disjoint, they don't overlap, but does the compiler look closely at the indexes in those ranges to figure that out? No, it does not. When you take a reference to an array, the whole array is considered borrowed. After we've taken a mutable reference for the first slice, A, the array is borrowed for as long as A is in use. So the array is not available and we can't take another reference to make B. So we get this compile error. Cannot borrow array as mutable more than once at a time. The first mutable borrow occurs here when we make A, the second mutable borrow occurs here when we make B, and the first borrow, A, is later used here when we call updateEach. So A is still in use when we try to borrow the array again. And check this out, it suggests calling split at mut to obtain two mutable non-overlapping subslices. So the compiler sees exactly what we're trying to do, and it has a very helpful suggestion. If I do what it suggests, here's what the code looks like. It's completely reasonable to want to split an array into multiple ranges and deal with them separately, as long as they don't overlap. So I call split at mut and pass in the index 6, which is the point at which I want to divide the array into two slices. That returns a tuple, so A is the slice up to but not including index 6, and B is the slice from index 6 to the end. Another nice use of tuples. Here's what that looks like in memory. We have our fixed length array containing 12 elements. When we call split at mut, the array is borrowed and we get back two mutable array slices, one for the first half and one for the second half. Split at mut will never return overlapping slices, so each slice has exclusive access to the elements it points to. One use for this would be if you have a big array to process, you want to do that processing in place in the array, and you want to spread the work out over multiple threads. You could hand each of these slices to a separate thread. And if you want to carve up the array into more than two pieces, you can call split at mut again on any mutable array slice to split it into smaller pieces. Split at mut is just one of many methods available on array slices, which raises an interesting question. How and where are these methods defined? Well, the core library, which is the platform-independent part of the standard library, has an impl block that looks like this. The T in angle brackets tells you this is a generic impl block, so T can be any type. The T in square brackets is the type we are implementing methods on. It's the self type for this impl block. And if you remember, T in square brackets is the unsized array slice. It is a type you cannot hold because it's an array of unspecified length. But you can have a reference to it. Now, look what happens when we have a method that takes self by shared reference. Len is a method that returns the number of elements. This ampersand self syntax is a shorthand. Let's expand it because I think that'll be a bit more clear. Ampersand self means that self is of type ampersand self with a capital S. Self with a capital S is an alias for the type we are implementing methods on, which in this case is t in square brackets. So let's substitute that in there to make it explicit. And now we can see that self is a shared array slice. So we're implementing methods on the unsized array slice, and a method that takes self by shared reference will operate on a shared array slice. Perfect. How about a method that takes self by mutable reference? The swap method takes ampersand mute self along with index A and index B, and it swaps the two elements at those positions. And we can expand that self parameter to make it obvious that this method operates on a mutable array slice. The split at mute method is the same. It takes self by mutable reference, which means it operates on a mutable array slice, and it returns a tuple with two mutable array slices. And thanks to the borrowing rules, the input, self, remains borrowed for as long as either of those output slices is in use. Now, the question I often get here is, how is split at mute implemented? Why is it allowed to return two mutable references to the same object? Isn't that breaking the rules? The answer is that split at mute internally uses unsafe Rust. It's allowed to use raw pointers to construct the two slices it returns. It presents a safe API because no matter what index you provide for the cut point between the two slices, those slices will never overlap. This method will never give you two mutable references to the same element in the array. Most of the standard library uses unsafe Rust. It's fine. Its whole purpose is to extend the capabilities of the safe language by providing primitives that can only be implemented in unsafe code, and it gets audited pretty carefully. What matters is that as the caller of a function like split at mute, I don't have to worry that I might be holding it wrong. The compiler will check how I use the references I get back from the function and enforce the borrowing rules. Okay, so now you've seen how methods on arrays and array slices are declared. Whether I'm holding a fixed length array or a variable length array slice, I can call any of those methods because the methods are actually declared on the unsized array slice, t in square brackets. That unsized type represents the concept of a contiguous sequence of elements in memory, and any type that can represent its underlying storage that way can be used with these methods. And now you understand why I put the array slice types at the intersection between the borrowed reference types and the unsized array. If you have a reference to an unsized array, then you have an array slice. These slices can handle variable lengths, but they don't own the elements they point to. They are borrowed references to array elements owned by someone else. What if I want an array that owns a variable number of elements? Well, for that we need heap allocation. The standard library gives us a type called vec, which owns a heap allocated array, and it can expose that heap allocation as an array slice, so it can be used with all those methods you already saw. Now, if you look up vec in the standard library, you'll see this. It's a struct with two generic type parameters. T is the element type, that's the one we care about. A is an allocator, and A equals global means by default, if you don't say anything about the second type parameter, you get the global allocator. I've never needed to use a different allocator, so let's keep it simple. We can ignore all that allocator stuff. Just think of vec as having a single type parameter t. We'll talk about generics properly in the next video, but what this says is that for any given type t, you can have a vec of t. Let's make a vec of integers. So our element type t is i32. Inside the vec namespace, we call the new function, which gives us an empty vec. There's also a convenience macro for constructing vecs. Invoking the macro with no arguments just gives you an empty vec. It's equivalent to calling new. And yes, macros can be used with square brackets around the arguments. The macro machinery doesn't care whether you use parens or square brackets or curly braces as long as they match. So this is just a style thing to make it look like the syntax for arrays that we saw earlier. And the vec macro accepts the same syntax. You can provide a comma-separated list of elements, or you can give a single value followed by a semicolon and a length. So this would initialize the vec with 1,000 zeros. And that works with any type that can be cloned. So you could initialize your vec with many clones of a string, for example. Now that we have a vec, let's put it to use. The point of using a vec instead of an array is that you can change its length at runtime. So in this loop, we're calling the push method to append some more elements. Vec is a struct that internally holds a pointer to a heap allocation. Each time we call push, it checks if there's space for the new element. If it needs to grow the capacity, it reallocates, which might mean moving all the existing elements to a new location in memory. And then it appends the new element. To access the elements, we can index into the vec with square brackets, just as if it was an array or an array slice. In fact, any method that's defined on array slices also works with vec. So for example, I can call the swap method, and it will swap the elements at those two positions in the vec. If I take a reference to a vec, that reference will coerce to an array slice, so I can use a vec directly with any functions that take array slices. With a mutable reference to the vec, I can call updateEach to add 100 to each of the elements. Or with a shared reference to the vec, I can call the total function we made earlier. I can also index with a range and pass that subslice to the total function. Notice what's happening here. When I take a reference to the vec, to start with I just have a pointer to the struct that's held on the stack by the local variable v. That struct contains a pointer to the heap allocation as well as the length and capacity. But when I pass that reference to a function that takes a slice, somehow we end up making a slice that contains a pointer to the elements on the heap along with the length. How did it do that? Does the compiler have special knowledge about vec? No, you could write your own type that does the same thing without any changes to the compiler. The magic is that vec implements a trait called deref. That trait says this type can work like a smart pointer, and here's how to dereference it to get at the elements the vec has a pointer to. On the Elements of Rust, the bottom half shows all the traits the compiler has special knowledge about. These traits give types the ability to work directly with syntax in the language as though they were built-in types. So right next to the deref trait, we also have the index trait that enables a vec to be indexed using square bracket syntax. This table only shows the traits that are built into the language. There are lots more traits in the standard library that don't need special support from the compiler, and you can build your own traits to represent interfaces in your own code. Traits are an extremely important part of the Rust type system, and we'll cover them in detail in the video after generics. Coming back to vec. Now that we have a type that owns a variable number of elements, we can write a function that calculates some values and returns them in a vec. For example, this function takes a number n and returns a vec containing the factors of n. You can't do that by returning a slice because a slice is just a reference. The data has to already exist somewhere that the slice can point to. I mean, okay, if you really needed to avoid dynamic allocation, you could do it like this. This time the caller provides a mutable array slice called buff for us to store the factors in, and we return a usize that says how many factors we stored in the buffer. But of course this requires the caller to know how much space might be needed. Sometimes that's fine, and it's worth it to avoid the performance hit of dynamic allocation. Let's go back to the previous version that builds a vec. What if we're calling this factors function a lot? Here's a main loop that calls factors with every value from 1 to 10,000. It's a bit sad that every time around the main loop we're creating a new vec, growing it a bit, then throwing it away. That's hitting the memory allocator way harder than we need to. How about we change this so we can reuse the same vec for each call to the factors function. So now factors takes a mutable reference to a vec called buff. And whatever factors it finds, it pushes them onto buff. Now in the main function we can move the vec outside the main loop. Each time around the loop we call the clear method, which sets the length of the vec to 0, but it keeps the capacity, it keeps the heap allocation. We reuse the vec, we never throw away the allocation, so we hit the allocator way less often. This is a useful pattern anytime you're using a dynamically allocated buffer. For example, if you want to read lots of lines of input, you'll probably use this readline method from the standard library. It takes a parameter, buff, which is a mutable reference to a string, so you can call it in a loop and reuse a single string for the buffer. And by the way, guess what you'll find if you go looking at the source for the string type? Yep, internally it's just a vec of bytes, but of course the API provided by String maintains the constraint that those bytes must always be valid UTF-8. Now, before we wrap this one up, I want to come back to this table that we've been building up over the last few videos. We've seen some types that can be implicitly copied because they just contain plain old data like scalars. We've seen some types like token that are move only because they represent unique resources that should never be duplicated. And we've seen this middle ground of types like string that do own a resource in the sense that there's a heap allocation involved, but they can be explicitly cloned if we need to. So, where do arrays fit into this picture? Well, for fixed length arrays, the rule is that the array is copyable if its element is copyable. So an array of integers can be implicitly copied. An array of strings can't be copied, but it can be explicitly cloned. And doing so just makes a clone of each string in the array. If the element type can't be copied or cloned, then of course you can't copy or clone an array of that type. Then we come to vec. A vec can never be implicitly copied because it owns a heap allocation. But if the element type can be cloned, then the vec can be explicitly cloned. That creates a new heap allocation and it clones all the elements. If the element type can't be cloned, then of course neither can the vec. From the audience retention numbers on the previous video, it looks like I did a pretty good job of bullying some more of you into trying the practice exercise, and it was great to get feedback from some people who said it was helpful, so thank you. The whole purpose of this channel is to help you learn, and it makes such a big difference if you spend a few minutes at the keyboard not quite knowing what to type. That's when the learning happens. I've made this easy. Just go to rustcurious.com/7 and press the button to open the code in the playground. In this exercise, we are implementing a very simple stack that contains chars. The definition of the stack type is provided for you, and yes, we could have just used a vec. A vec makes a great stack. It even has push and pop methods, but that would be cheating. The whole point of this exercise is to practice using arrays and slices, so we're doing this the dumb way. This stack has a buffer, buff, that's a fixed length array with enough space for 25 chars, and it has a usize, len, to track how many items are currently in the stack. So your first job is to write the new function that constructs an empty stack. It doesn't matter what char values you use to initialize buff, they'll get overwritten by the push method. Next is the len method, and this one is absolutely trivial, just return self.len. Then we come to the push method, which takes a char c. Just store the char in buff and then increment len. Don't worry about checking if the stack is full. When you store the char, if len is past the end of the array, then you'll get a panic, and that's what we want. The pop method returns an option because the stack might be empty, so you should check len before deciding what to return. Remember, option is an enum with two variants, some and none. The previous video is all about enums, or you can look at the unit tests if you'd like a syntax reminder. Once you've written new, len, push and pop, the first three unit tests should start passing. Next we have peek and peek mute. These are similar to pop in that they access the item that was most recently pushed onto the stack, but they don't remove it. They both return an option, which is none if the stack is empty. Peek takes a shared reference to self, and it returns a shared reference to the char on the top of the stack. Peek mute takes a mutable reference to self, and it returns a mutable reference to the char on the top of the stack. With these two implemented, two more unit tests will start passing. And finally we have asSlice and asMuteSlice. Both of these return an array slice containing all the items stored in the stack. Not the whole buffer, just the items stored, so the length of the slice should be the same as len. asSlice returns a shared array slice, asMuteSlice returns a mutable array slice. And this pattern of having two methods that are quite similar, one for shared access and one for mutable access, is pretty common in Rust. And that's it. With those done, all the unit tests should pass. I'd love to hear how you go with the exercise. The next video will be about generics, and the one after that will be about traits. We're getting to the point where we've seen all the major chunks of the type system, and that really opens up what you can do and what you can explore in the standard library. Rust is not a small language, there's a lot to learn, but in my opinion, all the pieces fit together really well. I hope you're enjoying these videos. I'd love to hear your thoughts if you'd like to drop me a comment. Until next time, stay curious.